What we have been doing up until this point is to take the Laplace transform of a function. So the Laplace transform of a function f of t, Laplace transform of a function f of t is the integral from 0 to infinity of e to the negative st multiplied by the function that you want to transform and then the t. And this one is equal to capital F of s. So this one is familiar. Alright, so now what we are going to do in this video is to take a Laplace inverse of a function. So first of all, the Laplace transform transforms a function from the time domain, right, from the time domain into the s domain or the complex domain. This s is a complex number, right? So this is what the Laplace transform does. Now the idea of the Laplace inverse is to take the function from the s domain back into the time domain, right? So here we are transforming a function from the s domain back into the time domain. So this is how it is written: the Laplace inverse of a function f of s, capital F of s, and this is equal to f of t, right? So taking this function which is transformed into the s domain and transforming that back into the time domain, and that is what we call the inverse Laplace transform of a function capital F of s. So this one transforms a function from the s domain, right? Transforms a function from the s domain back into the t domain, right? So the idea is very easy, right? And this one is built on the uniqueness of a Laplace transform of a function. It is built on the fact that the Laplace transform of a function f of t is unique, right? So the idea of the Laplace inverse is built on the uniqueness of the Laplace transform of a function f of t. So if we can recall, right, from my very first video, just for the purpose of illustration, the Laplace transform of just 1, the constant 1, this is 1 over s. The Laplace transform of e to the at, right, this is 1 over s minus what, a. This is based on the fact that x is strictly greater than a. And then the Laplace transform of this polynomial t to the n, this one is n factorial divided by s to the power n plus 1, right? So if we are given these Laplace transforms, what the Laplace inverse does is to transform these functions from the s domain back into the time domain. So the Laplace inverse of 1 over s, this one is equal to 1. That means it's going to return the function that is here, 1. Right, and the Laplace inverse of this one, which is 1 over s minus a, this one is going to return the function e to the at, the exponential function. And the Laplace inverse of n factorial divided by s to the n plus 1, this is going to return the polynomial to the nth power. Yeah, so this is the idea of the Laplace inverse. Laplace inverse is a very powerful tool because it allows us to solve differential equations with initial value conditions. So we will use the Laplace transform to solve differential equations with initial conditions, but before we do that, we must establish the concept of the Laplace inverse. So after building the concept of the Laplace inverse, then we can use that to solve differential equations with initial value problems. So I'll go ahead and solve some few examples using this Laplace inverse, and we know how it is applied in solving questions. So now I will go ahead and solve some examples. So the first one, question 1, let's say you want to find the Laplace inverse of this particular function. The function is 1 all over s into s minus 2, like this. What is the Laplace inverse of this function? So we are going to break this one down using partial fractions before we come back and take the Laplace inverse, right? So now let me do that here. This 1 over s into s minus 2, permit me to do it like this. I'm going to multiply top and bottom by 2, right? So I'm going to multiply this one by 2 all over s into s minus 2, like this. But I can't just multiply by 2, I have to nullify the effect by multiplying it by 1/2. And this one is equal to 1/2 outside. Then what do you have? So 1/2 outside, so permit me to subtract s to the numerator and add s. The net effect is 0 divided by s into s minus 2, like this. Right, cool. So this one is equal to 1/2 outside. Then you can break this one down into two different fractions. The first one is going to be 2 minus s divided by the denominator, which is s into s minus 2. And the second one is going to be plus s divided by s into s minus 2, like this. So that means that this one that we are asked to take the Laplace inverse of is 1/2 into, this one can be reversed into negative s minus 2, like this, divided by s into s minus 2, and then plus s all over s into s minus 2, like this. Now to see that there will be some beautiful cancellations. This one is going to cancel this one, and this one is going to cancel the s here. And now what do we have here? This one is going to be 1/2. What is left here is negative 1 over s plus 1 all over s minus 2, like this. Cool. So this one is now 1/2 into 1 over s minus 2 minus 1 over s, like this. So it means the Laplace inverse here, I am simply taking the Laplace inverse of this function. The function is 1/2 into 1 over s minus 2 minus 1 over s, like this. And the Laplace inverse operator is behaving the same as the Laplace operator, right? So a constant can be pulled out of the Laplace inverse operator. So we have 1/2, then the Laplace inverse of whatever is inside. So 1 over s minus 2 minus 1 over s, like this. Similarly, the Laplace inverse operator is behaving like the Laplace operator, so you can apply the linearity property. And this one is going to be 1/2 the Laplace inverse of 1 over s minus 2 minus 1/2 the Laplace inverse of 1 over s. We know these ones now, right? So in working the Laplace inverse of a function, we really have to know how to use partial fractions to break some complex functions down, right? So now when we come back here, what is the Laplace inverse of 1 over s? The Laplace inverse of 1 over s is just 1, because the Laplace transform of 1 is 1 over s. So this one is already 1/2 multiplied by 1. That's the Laplace inverse of 1 over s. What about this one? The Laplace inverse of 1 over s minus 2. If we come back here, the Laplace inverse of 1 over s minus a is e to the positive at. So that means that here our a in this case is going to be 2. So this means the Laplace inverse of 1 over s minus 2 is going to be e to the 2t. So this one is e to the 2t. So this one is 1/2 in front and then e to the 2t. Let me bring it closer. So 1/2 in front and then e to the 2t. Right. So that means that the Laplace inverse of this function, which is 1 all over s into s minus 2, this one is equal to 1/2 e to the 2t minus 1/2. Or simple, you can put it like this. You can just factorize 1/2 out. Then you have e to the 2t minus 1, like this. So you see that the Laplace inverse, we are able to transform the function from the s domain back into the time domain. This is built on the fact that the Laplace transform of this function is unique. All right. Cool. So this is the first example. The second one, let's go with the second one. So I'm going to give you this example. So question 2, we are asked to take the Laplace inverse of this function. The Laplace inverse of this function. The function is 3s plus 4. This is divided by s squared plus 4. This is the second one. So with this one, how do you take the Laplace inverse of this? So we are going to start off by breaking this one down into two different fractions. So the Laplace inverse is going to be what? The Laplace inverse of the first fraction, this is going to be 3s divided by s squared plus 4. This is the first one, plus the next one is going to be 4 all over s squared plus 4, like this. So we can break them down into two different fractions. Now, applying the linearity property of the Laplace inverse, this one is going to be the Laplace inverse of 3s all over s squared plus 4 can be written as 2 squared. Let's put it that way. And then the next one is going to be the Laplace inverse of 4 all over s squared plus 4 can be written as 2 squared, like this. All right, cool stuff. So here, this 3 is a constant. It's going to come out of the Laplace inverse operator. Then we are going to have this s all over s squared plus 2 squared, like this, plus this one. This 4 can be written as 2 times 2, right? So I'm going to bring the 2 here, and then the Laplace inverse of whatever is remaining at the top is 2, because 2 times 2 is going to give you 4, right? So this one is divided by the same denominator, s squared plus 2 squared, like this. So what are these ones, if we can recall from our Laplace tables? So you have to have these Laplace tables at the back of your mind. So the Laplace transform of a function, sine of at. Sine of at, this is equal to a all over s squared plus a squared. And the Laplace transform of the function cosine of at, this is equal to s all over s squared plus a squared. What this means is that if I'm taking the Laplace inverse, so here, if I'm taking the Laplace inverse of something like this, a all over s squared plus a squared, this is going to return the function sine of at. And if I'm taking the Laplace inverse of s all over s squared plus a squared, this is going to return the function cosine of at. Right, so this is what we have here. So if I can switch back, this one is going to be free, right? Looking at this one is looking like the cosine because we have s on top, and this one is looking like the sine because we have a number 2 on top, a constant, right? So this is free. The Laplace inverse of something like this is going to be cosine, but it is cosine of what? You have to determine that by the value of a. So a in this case is 2. So this one is going to be cosine of 2t plus this 2 out here. This one is going to be sine, right? Because we have a constant on top. So a constant on top and that same constant square at the bottom. So this one is going to be 2 sine of what exactly? The constant here is 2, and that is going to be 2t, like this. Cool. So that means that the Laplace inverse of what is the function? 3s plus 4, 3s plus 4 divided by s squared plus 4, like this. This one is going to be 3 cosine of 2t plus 2 multiplied by sine of 2t, like this. This one is the Laplace inverse of this particular function. What this means is, if you are taking the Laplace transform of this function, you are going to end up with this. So that is the idea of the Laplace inverse. Alright, cool stuff. So now let me go ahead and work a third example for you to see. Why not? So a third example, let me do it in white. So with a third example, we are going to solve this. We are going to have the Laplace inverse of this particular function, which is 4s minus 1. This is divided by 3s squared minus 12. What is the Laplace inverse of this? This is similar to question 2. So what I have to do is to split this function into 2 different fractions. So we have the Laplace inverse of 4s all over 3s squared minus 12. This is the first one, minus 1 all over 3s squared minus 12, like this. And using the linearity operator of the Laplace transform, Laplace inverse, I beg your pardon, this is going to be the Laplace inverse of 4s all over 3s squared minus 12, like this, minus the Laplace inverse of 1 all over 3s squared minus 12. Cool stuff. So using the property again, this 4 is a constant, right? I'm going to pull it out of the Laplace inverse operator, and that we have the Laplace inverse of s divided by 3 is common between this and this term. So I'm going to factorize 3 out. Why not? Then I'm going to have s squared minus 4. But 4 can be written as 2 squared, like this, minus the Laplace inverse. I'm going to do the same thing at the bottom for the second one. That is going to be 3 out, and then s squared minus 4 can be written as 2 squared, like this. Cool. So we have 4, and then this 1 over 3 is a constant. I'm going to pull it out. That's going to be 4 over 3 in front, and then the Laplace inverse of s divided by s squared minus 2 squared. This is the first one, minus this 1 over 3 is a constant. I'm going to pull it out. That is going to be 1 over 3 outside here. The Laplace inverse of 1 all over s squared minus 2 squared, like this. So these ones are, we know these ones, right? So let me refresh your memory with this. The Laplace transform of the sine hyperbolic of AT, this is equal to a all over s squared minus a squared, right? And then the Laplace transform of the function cosine hyperbolic of AT, this is equal to s all over s squared minus a squared. What is the meaning of this? This means that if you are taking the Laplace inverse of a all over s squared minus a squared, this is going to return the sine hyperbolic of AT, like this. And if you are taking the Laplace inverse of s all over s squared minus a squared, this is going to return the cosine hyperbolic of AT. Yeah, so this is what we have. So these ones, they look like the cosine hyperbolic and the sine hyperbolic, right? What we have here is s on top, so that one is going to be the cosine hyperbolic, and we have a constant here. But for the constant, we have this one is a and this one is a squared, but we don't have that here. This one is 2, but this one is only 1. So it means here we have to introduce 2 here. Yeah, there's no cause for alarm. What I can do is to clean this one, right, and then introduce 2. As simple as that. But I have to take it away by multiplying by 1/2 in front here, right? So this is the modification. So in the end, this is what you are getting. We have 4 over 3 in front, the Laplace inverse of s all over s squared minus 2 squared, like this, minus this one is now 1 over 6 in front, and then the Laplace inverse of 2 all over s squared minus 2 squared, like this. And now using these ones, we know that we are going to have the cosine hyperbolic and the sine hyperbolic. So this one is going to be 4 over 3. This one is the cosine hyperbolic of what? The constant here is 2. So cosine hyperbolic of 2t minus 1 over 6. And this one is going to be the sine hyperbolic of 2t, like this. Yeah, so this is what we have. So that means that the Laplace transform of whatever it is, Laplace inverse of 4s minus 1 divided by 3s squared minus 12. 3s squared minus 12, and this one is going to be 4 over 3 cosine hyperbolic of 2t minus 1 over 6 times sine hyperbolic of 2t. Cool stuff. So the meaning of this one is that if you are taking the Laplace transform of this is what you get in the S world. So that is for question 3. Now let me do a final one for you to see, right? So the final one, we are going to work something like this. Let me switch colors. So obsessed with switching colors. So now this is question 4, and the very last one. We are going to take the Laplace inverse of this function. So the Laplace inverse of 1 all over s into s squared plus 4, right? Plus 4, right? Yeah, so this is what we have. So how do you take the Laplace inverse of this function? So we have to use partial fractions to break this one down. Why not? So let's do that here. So now let me go ahead and then change colors. Then we are going to use partial fractions to break this one down. 1 over s into s squared plus 4. Using partial fractions, we are going to have a over the first one, which is s, and now because this one is a quadratic, the numerator is going to be a linear term, bs plus c divided by s squared plus 4. Cool. So now we have this. What we have to do is to do cross multiplication. So a multiplied by s squared plus 4, right, and then s multiplied by bs plus c, and this one is divided by the LCM, which is s times s squared plus 4, and then this is equal to 1 all over the same denominator, s into s squared plus 4, like this. Because the denominators are the same, you can just multiply by the denominator and you eliminate the denominator. So what is left is now the numerator, which is 1 equal to, expanding, we have ax squared s, I beg your pardon, plus 4a plus bs squared plus cs. So now we can group like terms, right? So we have 2 s squares. So the coefficient of s squared is going to be a plus b, s squared, right? And then the coefficient of s is c, and then the constant term is 4a, right? 4a. Cool. Now by comparing both sides, what do we have? By comparison, we have 4a, which is a constant on the right hand side, and that is equal to 1. The constant on the left hand side is 1. So we can solve for a, and a is going to be 1 over 4. Right. Now we can solve for c here. The coefficient of s on the right hand side is c. Right. What is the coefficient of s on the left hand side? That is 0. So c is equal to 0. And the final one, the coefficient of s squared on the right hand side is a plus b. What is the coefficient of s squared on the left hand side? That is 0. So if a plus b is equal to 0 and a is already 1 over 4, that implies that b is equal to negative 1 over 4. Right, so b is equal to negative 1 over 4, a is equal to 1 over 4, and c is 0. Now we can go back to our partial fractions and just plug them in. Right, so now the partial fraction, that means that 1 all over s into s squared plus 4. This one is equal to, a is positive 1 over 4. So you have 1 over 4 over s, right, plus bs plus c. B is negative 1 over 4. So negative 1 over 4 times s plus c. C is 0, and this is divided by s squared plus 4, like this. So this one is equal to 1 over 4 multiplied by 1 over s. And this one is minus 1 over 4 multiplied by s over s squared plus 4, like this. Cool. So now 1 over 4 is a common term. I'm going to pull it out, and now what is left here is 1 over s minus, this one can be written as s all over s squared plus 4 can be written as 2 squared, like this. So I think it is now safe to take the Laplace inverse, right? So that means that 1 all over s into s squared plus 4 can be broken down into this using partial fractions. Alright, cool. So now let's take the Laplace inverse. That means the Laplace inverse of 1 all over s into s squared plus 4, right? This one is going to be equal to 1 over 4 is a constant term. Then I'm going to have the Laplace inverse of this 1 over s minus s divided by s squared plus 2 squared, like this. Cool. So this one is going to be 1 over 4, and now using the linearity property of the Laplace inverse, we are going to have the Laplace inverse of 1 over s minus the Laplace inverse of s over s squared plus 2 squared. So this one is going to be 1 over 4, and then what is the Laplace inverse of 1 over s? Laplace transform of 1 is 1 over s. The Laplace inverse of 1 over s is 1. Minus, this one is the cosine term, right? Because you have s divided by s squared plus 2 squared. So this one is going to be cosine of what? The constant here is 2. So cosine of 2t, like this. So we are done. That means that the Laplace inverse of 1 all over s into s squared plus 4. This one is going to be 1 over 4 into 1 minus cosine of 2t, like this. So this one is the Laplace inverse of this function. The meaning is that if you are taking the Laplace transform of this function, this is what you get in the S world. So that is the idea of the Laplace inverse. So the Laplace inverse will simply take a function back into the T world from the S world. So it's just a reverse of the Laplace transform. And as I already said, this is very important in solving differential equation with initial conditions, which I will tackle in my subsequent videos. So subscribe to the channel, and then I'll see you in my next video as we continue deriving the Laplace inverse of exponential functions. So I will see you in the next video. Bye bye.